So in the previous lecture, we introduced the concept of measurable functions. Now we will define the integral of these measurable functions, and I will start from the beginning. So if you have seen that how to define the integral of a simple function which is non-negative, you can skip the first minutes of this video. So I want to define an integral of measurable functions. So I want to present the integration theory from scratch. So we will be working with a triple, which is a set, a sigma algebra of subsets of this set, omega, and then a measure which is defined in this sigma algebra. And we would like to define what I will represent by I of f, which is the integral of f. So remember, we defined simple functions. A simple function being a function which can be written as a finite sum from 1 to n of real constants multiplied by the indicator of sets, and where I'm assuming that these sets E1 up to En form a partition of the set omega of sets which are f measurable. So these sets Aj, Ej, they all belong to the sigma algebra f, and we are assuming that they are disjoint and that their union is equal to the set omega. Right, so this is simple functions, and if Cj are non-negative, I will define, so I'm defining here the integral of a non-negative simple function. So if f can be written through this sum, I will define the integral of f as the sum from 1 to n of Cj times the measure of Ej. And observe that this sum is well defined because all constants Cj on real numbers are non-negative. So it might happen that this sum is equal to plus infinity, that you have more than one term which is equal to plus infinity, because the measure of a set Ej can be equal to plus infinity. However, this is always well defined. So here is the definition of the integral of non-negative simple function, and we've seen in the previous lecture that this number is well defined. So eventually we can have, it might happen that same function can be written in two different ways, and we have seen that the definition of the integral does not depend on the specific representation of the simple function, so that this object is well defined. And from this definition we would like to extend this integral to the space of what we will call integrable functions. So let me just summarize what we will do in this lecture. So the first thing we will do is to consider a function f measurable with respect to the sigma algebra f, and I will represent this fact by this symbol that f belongs to the sigma algebra. So this means that f is measurable with respect to f, and f non-negative. So what we will do is we will consider a sequence of functions fn which are simple and which increase to the function f, and we will define I of f as the limit of I of fn. So there are many things we need to prove here in order to complete this step. First, we have to show that for any measurable function which is non-negative, there exists this sequence of simple functions which increase to f. Once we prove the existence of such sequence, there is at least one sequence which increases to f. So we will see that since this sequence is monotone, the sequence of the integrals is also monotone. So there is a limit. And we will define, but then we will have to show also that this integral of f does not depend on the sequence fn chosen. So this is a second result which we will prove. So once we prove the existence of a sequence of simple functions fn non-negative which converge to f which increase to f, and we prove that I of f does not depend on the chosen sequence, we would have reached a point in which we can define the integral of non-negative measurable functions. Then in the last step, so we will consider a function, a measurable function f. Recall that we represent by f plus and f minus the positive part of f and the negative part of f. We have seen that these two functions are measurable, so we will say that f it's an integrable function if both the integral of f plus is finite and the integral of f minus is finite, and then we can define as the integral of f as the integral of the positive part minus the integral of the negative part. So this is our road to the definition of what we mean by integrability, an integrable function, and what we mean by the integral of an integrable function. So this is the roadmap. Once we reach that point, we will prove properties of the integral. And then, so we will show that all properties I mentioned in 2 lectures ago are valid with this definition. So this is the roadmap, and the first step therefore consists in showing that for any measurable non-negative function there exists an increasing sequence of simple functions which converge to f. So this is our first result. So let me state the lemma. So let's consider a function f which is measurable and which is non-negative. And I want to prove that there exists a sequence fn which has 3 properties. For each n fn it's a simple non-negative function. Then that the sequence fn it's monotone, and finally that the limit of fn it's equal to f, and by limit I mean a pointwise limit, which means that for any x in omega fn of x converges to f of x. Okay, so this is the lemma, and the proof it's quite simple. I will represent the function. Let's say that we have here omega, here is r, so there is 0, and so what we will do, we'll fix n. So we'll take here is n. So if the function f has a value at some point x larger or equal than n, we will define fn of x to be equal to n. While we will divide this interval 0n in small intervals of type k to the power 2n, k plus 1 to the power 2n. And in this interval, kn, k plus 1n, say we'll take it closed in kn and open in k plus 1n, we'll define fn as equal to k over 2 to the power n. So let me define now rigorously fn. So fn of x will be equal to, as I said, fn if fx is larger or equal to n. And now if fx belongs to k over 2 to the power n and k plus 1 to the power divided by 2 to the power n, and in the range, so here k takes values between 0, so the first interval, since f it's non-negative, the first interval will be 0, 1 divided by 2 to the power n, and the last interval we want it to be just here, so here's n, so the point which corresponds here, k, the value of k which corresponds to this point is n to the power times 2 to the power n, right? Because that divided by 2 to the power n gives me exactly n. So we want k to range from 0 to n times 2 to the power n minus 1, right? So when the range of k is between 0 and n to the power 2n minus 1, these intervals start at 0 and they end at exactly n. Right? And so in this interval, we will set fn of x to be equal to k to the power 2n. Okay, so this is a way in which we can define. Another way is to say that fn of x, well, it's equal to a sum from 0 up to n times 2 to the power n minus 1. It will be equal to k to the power 2n if, so remember that this is the indicator function, if k divided by 2 to the power n, it's less than or equal to fx, which is smaller than k plus 1 to the power 2, k plus 1 divided by 2 to the power n, and it's equal to n if f of x is greater or equal than n, right? So here is our definition of the function fn. Observe that since f is measurable, this function here can be written, this set here can be written as the inverse image of the interval k divided by 2 to the power n, k plus 1 divided by 2 to the power n open. Since f is a measurable function, the inverse image of this interval by f, it's an element of the sigma algebra f, and therefore the same thing can be said about this set. This set, it's the inverse image of the interval n infinity, which also belongs to f because the function f is measurable, and therefore we have just represented fn as a finite sum of non-negative constants multiplying the indicator of measurable sets. So this proves that fn is non-negative and it's a simple function, right? Which is the first requirement of our lemma, right? So with this definition, we have just proved that the first requirement holds. Now we will prove that Fn it's increasing, so that Fn is less than or equal to Fn plus 1, and that the limit of Fn of x is equal to Fx. I will start with this last condition, which is the simplest one to prove. So let's go to that. So I just rewrote here the definition of Fn. Fn is equal to n if f of x is greater or equal than n, and it's equal to k divided by 2 to the power n if fx belongs to that interval where the range of kk goes from 0 to n times 2 to the power n minus 1. And what we want to prove is that Fn of x converge to f of x. Right? So there are two possibilities. The first one is that f of x is equal to plus infinity. Right? Well, in this case, for any n, f of x is larger or equal than n, and therefore this means that for that x, Fn of x is equal to n for any n. And this means that Fn of x converges to plus infinity, which is f of x. So this property holds in this first case. Now let's assume that f of x is finite, and let's choose some n such that, so let n0 and not to be such that f of x is smaller than n naught. And let's consider n larger or equal than n naught. Okay? So this means that since f of x is smaller than n, Fn of x is defined in this way. So you see that in this case, what is the definition of fx, of Fn of x? So this condition here means that k is less than 2 times 2 to the power n times fx, which is smaller than k plus 1. Right? This inequality is equivalent to that one, and this means that k, so it's equal to, let me represent by this symbol, the non-negative, the integer value of a real number. So k is the integer value of 2 to the power n times fx, which means that in this definition, what we have is that I can rewrite this definition in the following way. Well, if f of x is larger than n, then I'm defining Fn of x as the integer value of 2 to the power n times fx divided by 2 to the power n. Right? So because k, we have seen, it's exactly the integer value of this expression, and therefore Fn of x, it's the integer value divided by 2n. Well, but what does that mean? What do we know about the integer value? So remember, the integer value of a number, it's the largest integer which is smaller or equal than the number. So what we know about the integer value is that the integer value it's always smaller, less than or equal to the number. It will be equal if a it's an integer, and it's smaller than the integer value plus 1. Okay? Well, because by definition the integer value is the largest integer which is less than or equal to the number. So if we use that inequality here, we have on the one hand that the integer value, so we have two inequalities. The first one is that the integer value is smaller than the number, so the integer value of 2 to the power n times fx, it's smaller than 2 to the power n times fx divided by x. So this is always true. So we just shown that fn of x is smaller than fx. And here remember that I'm assuming that fx it's smaller than n. Okay, I'm assuming here that fx it's smaller than n. On the other hand, we know by this inequality that the integer value it's bigger than the real number a minus 1. So this is bigger than 2 to the power n fx minus 1 divided by 2 to the power n. So this comes from the second inequality, which means that fx, so let me rewrite here the conclusion. On the one hand, fn of x it's less than or equal to fx. So this is the first inequality. And then the second inequality, if I, cancel 2 to the power n with that 2 to the power n, I get that fx, it's smaller than fn of x. And then I have a minus 2 to the n, which goes to the other side, which gives me that inequality. Right? So we just proved that if fx is smaller than n, then fx is contained between fnx and fn of x plus 1 to the power 2 to the n, which proves that as n tends to infinity, fn of x converge to f of x. Right? Because, well, you see that you have lim sup, it's smaller, lim inf, it's greater, so that they in fact converge to fn of x. And this proves our claim, which was the third property we wanted to prove about this sequence fn of x. So up to this point, we proved that the sequence we defined, fn, it's a sequence of non-negative simple functions, and we just proved that the sequence fn converges to f. Now, it remains to show that this sequence is monotone, and this is our last claim that I will now prove. So I just reported here the definition, which can be written in this way. If fn of x it's smaller than n, then fn of x we've seen can be written as the integer part of this expression divided by 2n. Here I wrote the properties of the integer part of a real number. And now what we want to show is that the sequence fn it's monotone, which means that fn it's less than or equal to fn plus 1. Okay. So let's assume that fx, let's first discard the case in which fx it's equal to plus infinity. If fx it's equal to plus infinity, fn it's equal to n, fn plus 1 it's equal to n plus 1, and this inequality holds. So we can assume from now on that fx it's finite. So here I draw fx. So what may happen? Well, maybe fx it's larger than fn plus 1, n plus 1. In this case, fn will be equal to n, and fn plus 1 will be equal to n plus 1, and this inequality is satisfied. Now, it might happen that fx it's contained between n and n plus 1. Well, in this case, fn of x it's equal to n. And so I'm assuming here so that fx, so let me write it's greater or equal to n, but it's smaller than n plus 1. So in this case, well, fn of x we've seen it's equal to n. Now let's see what is fn plus 1 of x. And we'll just take here the definition. So this is the integer value of fx times 2 to the power n plus 1 divided by 2 to the power n plus 1. But since fx is larger or equal than n, the integer value of fx times 2 to the power n plus 1 it's greater or equal than the integer value of n times 2 to the power n plus 1 divided by 2 to the power n plus 1, and this is exactly n, which is fn of x. Okay. So in the case in which fx it's greater or equal to n but smaller than n plus 1, we have that fn plus 1x is greater or equal than fn of x. So this is very simple. So now I will erase that proof and I will concentrate in the case in which fx it's smaller than n. Right? So fx, now I'm assuming that fx is smaller than n, so we are in a situation in which here's n somewhere and here's n plus 1. Right? And first I will draw a picture and then I will give a proof. So the picture is as follows. Well, let's consider the integer k. So here's k divided by 2n, and here's k plus 1 divided by 2 to the power n. So f of x belongs to one of these intervals for some k between 0 and n times 2n minus 1. So what will happen is that in this case, by our definition, fn of x, the value of fn of x, it's exactly equal to k divided by 2 to the n. Now to obtain the value of fn plus 1, we have to consider intervals divided by n plus 1. So we will have here 2k, which is one interval. Then at some point, say here, we have 2k plus 1 divided by 2 to the power n plus 1. And here 2 times k plus 1 divided by 2 to the power n plus 1, which corresponds to this point. So here's our interval, our new interval in the scale n plus 1. This means that if f of x takes value in this first interval, f of n and fn plus 1 of x are equal to k to the power 2n, which can be also written as 2k divided by 2 to the power n plus 1. While if f of x takes value in this second interval, while f of fn of x is still equal to k divided by 2 to the power n, now fn plus 1 takes value equal to 2k plus 1 divided by 2n plus 1, which is greater than 2k divided by 2n plus 1. In any case, if it's either in this interval or in the second interval, we always have that fn of x it's less than or equal to fn plus 1. Okay, so this is the idea. This is a picture which explains, and now we have to turn this idea, this picture, into a proof. So let's prove it. Well, we know that if f of x is smaller than n, and therefore smaller than n plus 1, we know that fn of x is given by this expression. So fn of x, it's equal to the integer value of 2 to the power n f of x divided by 2 to the power n, and fn plus 1 of x, it's equal to 2 to the power n plus 1 times fx divided by 2 to the power n plus 1. And we have to show that fn of x is less than or equal to fn plus 1 of x, which means that this expression is less than or equal to that expression. Well, so let me erase. Oh, I shouldn't. So remember, here's k to n, and here's k plus 1 to n. So I will consider either the case in which fx belongs to the first interval or fx belongs to the second interval, and remember that at this point here it's 2k plus 1 divided by 2n plus 1. So I want to consider two different cases. Let's first assume that k divided by 2 to the power n, it's less or equal than f of x, which is smaller than k plus 1 divided 2k plus 1 divided by 2n plus 1. And let me rewrite this expression as 2k divided by 2n plus 1. So I'm first considering the case in which f of x belongs to this first interval, where k here, remember, is the integer value of 2n times fx. Well, in this case, f of x, fn of x, whose definition is here, so I have to write, so this means that since f of x belongs to that interval, it's also true that k to the power 2n, it's less or equal than f of x, which is less or equal than that, and this expression is less or equal than 2k plus 2 divided, so this is k plus 1 divided by 2n. And I wrote this inequality thus just to observe that if now I multiply f of x by 2n, 2n of f of x is between k and k plus 1, which means that this integer value is k divided by 2n, so f of nx, it's indeed equal to k divided by 2 to the power n, as I already observed, because k here, as I said, is the integer value of 2n times f of x. Well, but now let's observe that the value of fn plus 1 of x, well, fn plus 1 of x, it's 2 to the power n, the integer value of 2 to the power n plus 1 times fx divided by 2n plus 1. So if I multiply here all terms by 2 to the power n plus 1, I obtain that 2 to the power n plus 1 times fx belongs to the interval 2k plus 1. And this means, therefore, that the integer value of 2 to the power n plus 1 fx is equal to 2k. So we have here 2k, and we divide by 2 to the power n plus 1. And this is equal to k divided by 2 to the power n. And therefore, we obtain that if f of x belongs to this first interval, fn of x is equal to fn plus 1 of x. And therefore, the inequality which we are trying to prove it holds, it's satisfied, right? So remember that we are now proving that fn is less than or equal to fn plus 1. Right? So we just proved that if fx belongs to this first interval. So now let's assume that fx belongs to the second interval. So let me write that here. Now I'm assuming that fx belongs to the interval 2k plus 1 divided by 2 to the power n plus 1, and that this is smaller than 2k plus 2, 2k n plus 1, and observe that I can divide both expression here by 2 and get k plus 1 divided by 2n, which is the definition of this point. So I'm now assuming that fx belongs to that interval. And of course, 2k plus 1, it's greater or equal than 2k divided by 2 to the power n plus 1, which can be written as k divided by 2n. So let's compute fn of x in this case. Well, in this case, f of x belongs to the interval k divided by 2 to the power n and k plus 1 divided by 2 to the power n, which means that 2 to the power n times fx belongs to the interval k plus 1, and therefore that the integer value of 2 to the power n fx it's equal to k. So here again, fn it's equal to k to n. Well, this we know because fx belongs to that interval, so we knew that already. I just checked it once again. But now let's look at fn plus 1. So to compute fn plus 1, we have to compute the integer part of 2 to the power n plus 1 times fx. So if I multiply now this expression by 2 to the power n plus 1, we obtain that 2 to the power n plus 1 times fx, it's contained in interval 2k plus 1 and 2k plus 2. This means that the integer part of 2n plus 1 times fx it's equal to 2k plus 1, and therefore that fn plus 1 of x it's equal to 2k plus 1 divided by 2n plus 1. And here we obtain that fn plus 1 it's bigger than fn fx. So that this inequality holds also. So as we said at the beginning, if fx belongs to the first interval, fn and fn plus 1 are equal, while if fx belongs to the second interval, then fn plus 1 it's strictly bigger than fnx. But in any case, we have always the inequality, and this completes the proof of this lemma. So up to this point, we proved that if I have a function f, which is measurable and non-negative, I can find a sequence fn of functions which are simple, non-negative, and which increase to f. So this means that the sequence is monotone and it converges pointwisely to f. Okay. Well, since we defined already the integral of a simple function, and since, as I will show, if I have two simple functions f and g such that f is less than g, we will show in a second that the integral of f is smaller or equal than the integral of g. So this means that this sequence is non-decreasing, it has a limit, so I can define the integral of f as the limit of this sequence. Right? But of course, it's conceivable that there is another sequence, gn, which also is formed by non-negative simple functions which increase to f, and therefore I will have my second claim is that this limit does not depend on the chosen sequence. So first let me show this inequality, and then let's prove that this limit does not depend on the sequence. Well, this inequality is very simple. Let's take a simple function f. So f can be written as Cj Ej where Ej, remember, the sets Ej belong to the sigma algebra F, and the set Ej form a partition of the set omega. In the same way, let's consider another simple function where again fk belongs to the sigma algebra F, and the partition fk is equal to omega. Well, and let's assume that f is less or equal than g, and let's prove that I of f is less or equal than I of g. Right? Well, this is very simple, because if Ej intersection fk, so let's take two sets, Ej and fk, either they have their intersection is empty or their intersection is not empty. In the case in which the intersection is not empty, right? Well, taking a point in this intersection, since Ej and fk are partition, we see that f of x is equal to Cj, and g of x is equal to dk. Since f is smaller than g, we obtain that in this case we have that Cj is necessarily less than or equal to dk. Right? Now, we can rewrite so g and f. I can always use the fact that Ej and fk are partitions to rewrite g and f as a sum g from 1 to n, k from 1 to m, dk, the indicator of Ej intersection fk. And I can also write f as a sum g from 1 to n, k from 1 to m of Cj, the indicator of Ej intersection fk. Okay? So these are alternative forms for the simple function g and f. So if I use that alternative form, we have proved already that the integral of g of a simple function does not depend on the representation. So I of g can be written as the sum n m of dk mu Ej intersection fk. Right. Now at this point, well, if Ej intersection fk is the empty set, this measure is equal to 0, and this expression it is equal to 0, so it's also equal to Cj mu Ej intersection fk. Right? So my claim is that dk times the measure of ej intersection fk, it's equal to cj times the measure of ej intersection fk. Why? Well, either ej intersection fk it's an empty set. If ej intersection fk it's an empty set, mu of an empty set is 0, so dk times 0 it's 0, and for similar reasons cj times mu of this set it's equal to 0, therefore these two expressions are equal. On the other hand, if ej intersection fk it's not empty, we have seen that cj is less than or equal to dk. So this expression, in this case, dk is greater or equal than cj, and therefore this sum is greater or equal than the sum we obtain by replacing dk with cj. Once we replaced dk by cj, we see that this sum corresponds to the integral of f when f is represented in this way. So this is equal to the integral of I of f, and therefore I of f is indeed less than or equal to I of j, as I claimed. So this shows that the integral is monotone if we take non-negative simple functions, and so this sequence it's monotone, it has a limit, and now all what we need to do is to show that if we take another sequence of monotone functions, of simple functions which are non-negative and increase to f, we obtain the same limit. And this is our next theorem. So in order to show that the integral of f is well defined by this formula, I of f equal to the limit of I of fn, right? We have to prove the following theorem. So let's consider two sequences, fn and gn. Fn, it's a simple function, as well as gn. They are non-negative. They are monotone, so both increase to f. Right? So these are our assumptions. We consider two sequences of simple non-negative functions which both increase to f, and we want to show that the limit of I g of n, which always exists, can be plus infinity, but it exists because we've seen that I g of n is an increasing sequence, non-decreasing sequence, that this limit is equal to the limit of I of fn. Right, so this is our the theorem we would like to prove, and in fact what we will prove, and so this is well, a clever idea that will simplify the proof of this expression, is that in fact it's enough to show that if you have a sequence fn of non-negative simple functions and g a simple function, non-negative, and if g is less than, so, and suppose that this fn forms a monotone function, sequence of increasing, well, monotone sequence, pointwise, so this means that fn of x is less than or equal to fn plus 1 of x, therefore fn has a limit. So now I assume that g is smaller than the limit of fn. So this means that this is also pointwise. I assume that g of x is less than or equal to the limit in n of fn of x for all x. Then we claim that I of g is less than the limit of I of fn. So this is what we want to prove, right? And what I claim is that if we prove this statement, then the theorem follows. But the main difference between this one and this one is that now we are assuming, we are comparing a limit of simple functions with a simple function, right? So we will use strongly the fact that g is a simple function in order to prove this result. And what I claim for the moment is that the theorem is a consequence of this result, and this is very easy. So assume that this statement holds, and recall the assertion of the theorem. So I have here gk, it's a simple function for any k. Gk increases to f, so gk it's smaller than f, and f it's the limit of the simple functions fn. So we are exactly under the assumptions of this remark. Fn are non-negative simple functions. Gk it's a simple function which is also non-negative. Fn it's monotone. Gk it's smaller than the limit. We just proved it. Then it follows that the integral of gk by this observation or by this lemma, it's smaller than the limit of I of fn. This is exactly what. So let me call this as a lemma just to identify it. Right? So the lemma is stating that I of gk is smaller than the limit of I of fn. And this is true for any k, so I can take the limit in k and deduce that the limit of ijk is less than or equal than the limit of I of fn. And of course this is symmetric, so we can replace g by f and f by g to get the reversed inequality, and therefore that the fact that both limits are equal. So in order to prove that theorem, it's enough to prove this lemma, and this is what we will prove now. So let's prove that if I have a sequence of non-negative simple functions fn, which is monotone, so it's non-decreasing, and I have another non-negative simple function g, and g it's less than the limit of fn, so fn being increasing sequence, it converge. So let's assume that g is smaller than the limit. I want to prove that I of g is smaller than the limit of I of n. And the main tool here will be that mu it's a measure, and therefore it's continuous from below. So first, I know that g is a simple function, but I will make the assumption that g is in fact the indicator of a set E times a constant C. So E, it's an element of F, and I will prove this statement in this very simple case, and by using this result I will extend it to all non-negative simple functions using the linearity of the integral which we proved at the beginning of this lecture. So let me assume for the moment that g is equal to some constant c, which is non-negative, times the indicator of a set E, which belongs to the sigma algebra. Right? Well, there are two cases to consider. Either c is equal to 0, but if c is equal to 0, then I of g which is equal to c times the measure of e. We've seen that 0 times plus infinity, it's 0 by convention. So even if the measure of e is equal to plus infinity, this integral will be 0. And if the integral of g is 0, there is nothing to prove, because fn being non-negative simple functions, the integral of fn is larger or equal than 0, and therefore this inequality is trivially satisfied. So in the case c equal to 0, there is nothing to prove, and therefore I may assume that c is strictly positive. So let's now consider the case in which c is strictly positive. If c is strictly positive, let me fix an epsilon which is between 0 and c, and which will be very small. It will converge to 0 at the end of the proof. So let me consider the function fn. Fn is a simple function, so if I multiply fn by the indicator of d set E, I obtain a new simple function, which is, of course, less than or equal to fn. And it's also clear that this sequence, that the limit of this sequence will be larger or equal to g, so that the limit in n of the indicator of E times fn will be larger or equal to g, because either, if you take a point in omega, either it belongs to E, in which case E, the indicator of Ex fnx, it's equal to fnx, and fnx converge to something which is larger than g, therefore this inequality is satisfied, or x belongs to E, in which case this expression is 0, but g is also 0, and therefore this inequality is satisfied. So we know that fn, it's a simple function, so we know that fn it's equal to some k going from 1 up to mn of c k n, or maybe n k, times the indicator of some set f n k. And now if I multiply that by E, I obtain that this is just a new simple function, which is c and k times the indicator of f and k intersection E. Now let me denote by an. This sets the points in E such that fnx is greater or equal than c minus epsilon. What do I know about this set an? Well, I first claim that these sets an are increasing, so that an it's included in an plus 1. Why this is true? Well, take a point in an. So this is a point in E for which fnx is larger or equal than c minus epsilon. Since the sequence fn is increasing, fn plus 1 it's larger than fn, and therefore fn plus 1 it's larger also than c minus epsilon, which means that x belongs to an plus 1, proving this inequality. Then my second claim is that, well, if I take the union of all sets an, what I get, it's exactly, I claim, the set E. Well, there is one side of this inequality which is very simple, is that the union of an it's contained in E. Why? Because, well, each an it's contained in E, and therefore the union is contained in E. So now let's check the reverse inequality. Well, let's take a point in E. If we take a point in E, g of x it's equal to c. But fn of x, it's larger than the limit of fn of x, it's larger than g of x, which is c, which means that the limit of fn, it's x, it's larger than or equal than c, which means that there exists some n naught for which fn naught x, it's larger than c minus epsilon, and therefore for all n larger than n naught, we will have that fn, it's larger, and therefore x belongs to some an, which proves the reverse relation. So we just showed that E, it's in fact equal to the union of an. Now, let us write the following. We have I of a fn. By the inequality, since fn, well, it's larger than fn times the indicator of an, this is larger than I fn, the indicator of an. Right? See, here I'm using this same relation but replacing E by an. And we have seen that if we have a function which is bounded by the other one, then the integral is also bounded. So we have this first inequality. Now on the set an, fn it's larger than c minus a epsilon. This means that, well, let me write it here. On the set an, fn it's larger than c minus epsilon an. C minus epsilon times the indicator of an, it's a new non-negative simple function because epsilon was chosen between 0 and c. So c minus epsilon, it's strictly positive. So again, we have a simple non-negative function which is bounded by another one, which means that the integral of this expression is bounded by the integral of that one. So we have a new inequality, which is that the integral of fn it's larger or equal than the integral of this simple function. But now observe that what is the integral of this expression? Well, it's c minus epsilon times mu an. So from this expression, we can conclude that, let me erase this piece of the blackboard. So we just proved that c minus epsilon, let me take the limit of mu of an. So this limit exists because an it's an increasing sequence, so this is an increasing sequence. It's larger than the limit of I of fn. But now an it's increasing to e, so this limit here it's mu of e. So here I'm using the fact that mu it's continuous from below at the set e. Now there are two possibilities. Either mu of e it's equal to plus infinity. If mu of e is equal to plus infinity, since c minus epsilon is positive, strictly positive, this means that the limit of I of n it's plus infinity, and therefore this inequality is trivially satisfied. There is a second possibility, is that mu of e is finite. So in case mu of e is finite, what we have is that c times mu of e minus epsilon times mu of e, it's less or equal than the limit of I of fn. Well, but c times mu of e, since g it's equal to c times the indicator of e, the integral of g is exactly equal to c times mu of e, which is there. So this is equal to let me write it here, I of g minus epsilon times mu of e. So what did we obtain? We obtained that I of g minus epsilon mu e, it's less than the limit of I of fn. But since we are assuming that mu of e is finite, letting epsilon tending to 0, we obtain that I of g is less or equal than the limit of I of fn as we claimed. So this completes the proof of this statement in the case in which the function g is equal to c times the indicator of a set E. Right, so now let's complete the proof. We already proved this result when g is equal to c times the indicator of a set E. Now since g is not a non-negative simple function, g can be written as a sum from, say, k from 1 up to m of ck, the indicator of ek. Well, by linearity, the integral of g it's equal to the sum of the integral of ck, the indicator of ek. But now let me consider the function fn multiplied by the indicator of the set ek. Well, what I claim is that the limit of this sequence is greater or equal than ck, the indicator of the set ek. Well, because there are two possibilities, either take a point x, either it belongs to ek or it doesn't. If it doesn't, it's 0 and 0, there is nothing to prove. So if it belongs, we have on the, so let's take now a point in ek. On the left hand side we have the limit of fnx, and on the right hand side we have ck. But ck, it's the value of g on the set ek. So we know that in this case ck, which is g, it's bounded by the limit of fn, and therefore this inequality holds for points x in ek. And therefore I can now use the first part of the proof. We have here a sequence of simple functions which is monotone and whose limit is greater or equal than ck times the indicator of ek, and therefore the integral of this simple function is bounded by the limit of the integral of these functions. So I'm just rewriting this fact here. Right? By the first part of the proof, we know that for each k, the integral of this simple function is less than or equal than the integral, the limit of these integrals. Well, now this sum is finite, so I can exchange the limit with the sum to obtain that the last term is equal to the limit of the sum from 1 to m of I fn ek, the indicator of ek, and use again the linearity to say that this is the limit of the integral of the sum from 1 to m of fn ek. So remember that ek forms, since g is a simple function, we expressed g through a partition of the set omega by elements of the sigma algebra. So ek forms, we can assume that ek forms a partition, and therefore when I sum over k all the indicators of ek, I get 1, and so this is exactly equal to the limit of the integral of fn, and therefore we have that the integral of g is less or equal than the limit in n of the integrals of fn as we claim. So we've seen that we used here linearity, and in the first part of the proof we used the fact that mu it's continues from below to prove this result. So we just proved that if I take a non-negative measurable function, we can define the integral of this function f as the limit of I fn, where fn it's any sequence of simple functions which is monotone and increases to f. So in this way we have a definition of the integral of non-negative measurable functions. Now I want to extend this definition to functions which are not necessarily non-negative. So let me take a function f. Well, we know that we have shown that its non-negative part and its negative part, its positive part and its negative parts are measurable and they are non-negative. So definition, I will say that a measurable function is integrable well if both its positive part and its negative part are integrable. So both if I of f plus is finite and I of f minus is finite. Right? And I will define the integral of an integrable function I of f as the integral of its positive part minus the integral of its negative part. Right? So this is the definition, the final definition of the integral. If you consider a function f, you take both its positive and its negative parts. You know how to define the integral of its positive and negative parts. If both are finite, you just define the integral of f as the difference of these integrals, and that concludes the definition of the integral. So now what I will do in the next lectures is to prove properties of the integral of an integrable function.